anytime you see a delta x, you can have an h, but otherwise final answer is 7. Number 38. Oh! Oh! We did this one yesterday together in class. I just didn't graph it. Oh! Okay, can we just talk about 38 real fast? I'm sorry, just real fast. Not all of them, just 38. I did it for you yesterday in class. Because what kind of function is number 38? Absolute value. Can you open up your notes to where we were talking about differentiability and continuity, right? Differentiability and continuity. Anybody's birthday today? I have a birthday message for you. Who's the closest birthday? Mariah. Mariah's a Sunday? Yeah. Anybody celebrate here?
Yeah, mine's July 2nd. So I said.
What? 22nd? 26th.
Yeah, nobody cares.
Our half birthdays are.
We'll celebrate your half birthday.
My birthday is coming up in October.
January 2nd.
Oh. Well.
We still won't even be in school that night.
Yeah, we still.
No, that is, but like it's New Year's. I mean, you might be in
No one
might not be in school.
Gone someone. He's never someone.
Somewhere will be much birthday.
My mom
Sorry.
That was not crazy.
Guess what?
What?
I got my shift covered, so I can go to the bond. That was fun. This was fun. No one covered.
All right.
I'll be in more coffee.
That's the graph. So absolute value yesterday. Are you in your notes where we talked about continuity differences?
Yes.
Awkward. I did not get to update all the forever cards. I actually ended up being late to hang out with a friend yesterday. And then I graded till late. And then I was into it this morning, but then I was doing your test that you're getting back today. But coming back. Even though those forever cards aren't updated, number 6 is, but the other ones aren't. Guess which forever cards are updated?
1 through 5.
The online ones.
On that one.
The online ones, which is in your class notes folder underneath class resources. You can find in Classroom or in the website. But on that continuity differentiability card, or right below it, didn't we talk about sharp points?
Yeah.
And didn't we talk about the absolute value function?
Yeah.
And how the absolute value function is a piecewise? Now this guy's been shifted. I get it. I get it. But still, just the general absolute value. He can be x sometimes, he can be negative x sometimes. For positives, he just stays the same. For negatives, he flips. Are we kind of getting okay with that? Hopefully. But then we talked about how each of these pieces are lines, and we know slopes of lines. Derivatives are slopes of lines. We know slopes of lines. We can look at it and say, oh, it's y equals mx plus b. And what's the slope for the first piece, guys?
1.
Positive 1.
Okay.
And what's the slope for the second piece? Negative 1. Now slopes. Aren't slopes the derivative? Remember notation yesterday? You're deriving this guy, and what do you get? 1 and negative 1. When? Well, you get 1 for all the positive numbers. You get negative 1 for all the negative numbers, but why haven't I said or equal to 0? Are they agreeing on either side? 0.00001, negative 0.00001. Are they coming together? No. But guys, here's the dealio. How do you graph the derivative? Well, don't you just graph y equals negative 1 up to 0, and then y equals 1 after 0? It's right there. Y equals 1 is a constant function for all positive x's. Y equals negative 1 is a constant function for all negative x's. And from our basic graphs, what does a constant function look like? Do you see now how it's broken at 0? And why the derivative does not exist? Because the limit from either side of the derivative function, you can even think of f prime of x. The limit from either side does not agree, therefore the derivative does not exist at 0. Yeah.
If we said do not exist, we also have to show the graph.
Well, here's the struggle. The derivative only does not exist, or in context of your homework, this guy is only not differentiable at 0. Everywhere else, he's fine. So when we're talking about our forever card in our notes, and it was back a couple pages, right? When we were talking about that forever card, this guy. When I say not continuous is not differentiable, guys, is a function ever like not continuous everywhere, or are they just like special points where it's not continuous? Yeah, so they're just special points where it's not differentiable. Does that make sense? So a place where the function is not continuous, at an x value where the function is not continuous, like a vertical asymptote, a hole, or like we just saw a break, although that would be a big derivative, then the derivative does not exist at that point, but it's okay everywhere else. And even if the original function is continuous, like a cube root or a tangent inverse, or like a square root, although it doesn't look quite like that, or an absolute value function, those are continuous functions. The domain is all real numbers, except there are still places where the derivative does not exist, but it's only at, like in this one, at 0, or in this one, at 0. But in the one that we were just looking at, it's not at 0. Isn't it not differentiable at, was it 4? Where was that guy shifted over? So is my graph of the derivative technically right? Yes!
Yeah.
For him, but not for him. So what would I change to make it applicable for this guy? I would just shift him. No, that's going to be in the way. I would just shift him over here and say, okay, so the slope everywhere above 4 is positive 1. And the slope everywhere below 4 on the left of 4 is negative 1. That's the only change you have to make. The only change you have to make. Because the slope of this line is positive 1 for all of that, and the slope of this line is negative 1 for all of that. And so I graph negative 1 and I graph positive 1 and I say, not agreeing, oh, that's right. Derivative does not exist. Does this one make sense? What is the slope? Negative 1. What is the slope? Positive 1. We'll get back to the other guys later. We will, I promise. Let's keep reading. Let's get back to 40. That's another graph one, right? We'll get back to 40 in a second. The 738, 39, 40, yeah. Number 46. F of x was x cubed and c was negative 2. F of x was x cubed and c was negative 2. Wait, is that something where you were looking at like a limit formula and trying to pull stuff out? Yeah. That's a great question. Out of the entire homework, maybe besides what we just did with the graph of the derivative, this is the most applicable to the AP. I'm saying that because some BCKs might be telling you something like Joe Tan said last night. Out of that entire homework, the majority of it is insignificant or is, I don't know, useless, or is, I don't even know what else he said. But it's not useless. It's not. What was the problem for this? The limit as? Wait, is it h or x?
It's delta.
Okay, so we could say like h. So then, did you guys have something like negative 2?
Plus c.
Why is this hard? It might have not been hard for some of you, but why was this one kind of hard to see?
The 8 is that.
Yeah, where did I tell you to look for f of x? Right here. But the problem is, I don't know. So then we have to come back and say, okay, help. Do you guys see your a plus h being plugged into a function?
Yeah.
Your a is equal to negative 2. So we could have figured that out. We could have also said, okay, hold on. 8 is negative 2 something. Oh, it's negative 2 cubed. Oh, I get it. What was the function this was plugged in? What was the function negative 2 was plugged into? There's our x cubed. So sometimes it takes a little bit more work to figure out what's in this spot, because sometimes something has been simplified. And so you're like, well, I don't know. They're not going to make it look all gross and like negative 2 cubed. They'll say it's 8. So we kind of have to be careful. Sometimes we have to look, because f is technically in both of these spots, but this one has an a plus h, this one has an a. So sometimes you have to kind of look deeper to see it. But anyway, great problem, because what is this all having you do? It's on this side of a limit as h goes to 0 of f of a plus h minus f of a all over h. What is that? F prime of who's a? So as soon as we start section 2.2 basic derivative rules, and we remind ourselves, learn, that you can take a derivative of a function with a power rule. What's the power rule for this guy?
2x. 3.
Bring down the 3, subtract a power. If I just need to find this, do I even have to do it? Oops, do I even have to do it this way, how I cube of a polynomial?
No.
No, I can just say that. Plug it in. Which one looks easier? Multiplying this guy by himself 3 times, then simplifying my limit, and then plugging in h is 0, or doing a power rule and saying plug in -2. Answer my question first. Which one's easier?
The bottom one.
The second one. Okay, Adam, what's your question?
Okay, so in the first one is finding the slope at -2 at one point. Why was the result different when you used power rule?
What do you mean? This one?
12 and then it was. Oh wait, never mind. I was thinking of.
And that would be 1, 3, 3. That's okay. I like proving it to not just you, but other people. Because if I was to do Pascal's triangle, then if I was to cube this guy, it would be -2 cubed times h to the 0 plus 3 times -2 squared times h to the 1 plus 3 times -2 times h squared plus h cubed. 1, 3, 3, 1. Yeah. And that would be the cube thingy. And then I have the plus 8. And then I have the all over h. And then I would go ahead and that would be -8. And that would be 4 and 3 is 12. And that would be, that's -2, so that'd be minus 6h squared. And that'd be plus h cubed plus 8. The 8's cancel. I have all over h. Oh, by the way, still taking a limit.
Oh, I see.
I can.
I see you forgot 12H.
Oh, is that what I did? Where is he? Oh, yeah, it's a little h. I can pull out an h and an h and an h, and I end up with 12 minus 6h plus h limit as h goes to 0. And my final answer is, woo! Can you get 12 doing this? Yeah.
Possibly.
Which one's easier?
The power rule.
That's where we're going in section 2.2. You guys have hung in there. Let's make sure we have no other evens that we need to grade. Because I'm feeling like we might. Yes, we do. 66, the final answer is -3/16. 66, the final answer is -3/16. 76, differentiable everywhere except for the discontinuity. So everywhere except x equals 3, which means you could say that it's differentiable everywhere, but x can't be 3. Or as I saw earlier this morning, you could use interval notation, -infinity to 3 with a union of 3 to infinity. That excludes 3, but so does that. Adam, you had a question?
Did you go over 66?
Was plugging in okay?
Oh, for the buff. Oh, never mind. I see what it is.
Because I would multiply top and bottom by 4x over 4x.
Yeah.
And I would distribute.
I put f of x in the denominator.
Ooh, yeah, that would mess you up. That would mess you
I
up.
got almost.
They were using, you guys didn't have to use that form though, I don't think. Did they give you the f of x minus f of a form, or did they just say use a definition?
Use the alternate.
Okay, so the other way you could have gone would have been the limit as h goes to 0 of f of a plus h, which would have been your 4, plus h minus f of a all over h. You could have also done it that way. That also would have equaled f prime of 4. But if you were to do that, you would have needed, just because I know that some of you might have done this different ways, you still would have needed to simplify your complex fraction. Does that make sense? One way or the other? Both of them should get you to -3/16. 76, once again, everything was good except for that vertical asymptote, and where a function is not continuous, it is not differentiable. Number 78 was good everywhere but 1. It was good everywhere but 1. You could have also used the union notation, -infinity to 1 and then 1 to infinity. There was a break there, so derivative does not exist. There was a break there, so derivative does not exist. And now it feels like we're done with the evens. Woo! Alright, that was a little bit rough. That was a little bit rough. Okay, let's go back to, if you guys don't mind, first of all, those graphs, because you guys had to do number 40. I don't think it's bad for us to talk about. Well, hold on, that was just evens. Did I give you all of them?
Yes.
Because I'm cool like that. Alright. This is one that Adam and I were talking about earlier. derivative look like this? Why would the derivative look like this for number 39? I think he's kind of, I'm going in the order of easiest to hardest, I think. 37 is the easiest? Yeah, maybe. What are my derivatives, or what are my slopes doing? They're uphill slopes, right? Uphill slopes, so positive slopes, so above the axis. What's happening as the x values get closer and closer to 0? My slopes are getting steeper and steeper, closer and closer to what?
0.
Zero's like this. Getting steeper and steeper and steeper. Now, what are the slopes doing as I go this way? If it's going to keep on. That's leveling off. Leveling off would be going to 0. Oh, going to 0. What's going this way? Downhill slopes, negative slopes, below the axis slopes, going closer and closer to 0. Oh, closer and closer to 0, closer and closer to 0, but getting steeper and steeper with the positives and getting steeper and steeper with the negatives. Yesterday we saw vertical tangent lines are infinite slopes, so I knew that the derivative had to have a vertical asymptote. I saw uphill, so I knew positives going to that vertical asymptote, and then this one I saw downhill going to that vertical asymptote, and when I saw it leveling off, I'm like, haha, it's like a 1 over x graph, kind of. Kyle, why did you say this one was easy, even though it wasn't for everybody? But for you, why was it easy?
Because I might or might not have used the power rule, knowing that that's x squared.
Oh, whenever you take the derivative of a x squared, it just whoop, whoop, and it becomes a line, right?
Yes.
And what kind of x squared was this? A positive one or a negative one? A positive one. So what kind of line am I going to have? A positive one. So do I just write it? Draw a line?
No.
Yay!
Good.
Because, what do I know about the slope at 4? Yeah. If the up and down slope is infinity, this slope is 0. Wait a minute. So the derivative, remember, had to be at 1 when it equaled 1, or had to be at negative 1 when it equaled negative 1. It had to be going to infinity when it was getting steeper, or going to 0 when it was getting leveled off. Why do I know the derivative has to hit right here? What's the y value on the x-axis? 0. And what's the slope at 4? So I knew it had to be there. Now I can go ahead and be like, yeah, there it is. Wow. Make sure it goes through 0. Yeah. But still. Has to go through 0. Has to go through 0. It has to be a positive line. But besides that, okay. So number 40. Do you guys know why I'm going to put a 0 right here for my derivative? Because the slope there is 0. So my derivative y has to equal 0. I have to have a 0 of the derivative when the slope goes flat on the original. Doesn't matter where it is. It matters the slope. Right? Now, hold on. What's happening after that? Downhill. Downhill means going like negative, right? Wait, why am I going to do this? And why am I going to do this for my derivative? What are the slopes going to? Infinity and to
Beyond.
infinity. And what has to be happening in a graph for the function to be able to be going to infinity? There has to be an asymptote. So I knew when it meaning the slope goes vertical, that's an asymptote. And when the slope goes vertical, that's an asymptote. Now I just need to figure out, okay, am I getting there with a positive infinity or a negative infinity or a negative infinity and a positive infinity? Just ask yourself, uphill or downhill? What kind of slopes? These are uphill, right? If you were climbing this guy left or right?
Okay.
Uphill. So uphill means I'm going positive. How about this guy? Downhill, which means I'm going negative. I don't know, something like that. It's kind of like a backwards tangent, a cotangent that's been shifted, like a x cube that's been flipped. Like that. Something. Are these easy? No. But, hold on, real quick. Did it help if we actually knew what the function was and we knew what his derivative was? or if we knew what the function was kind of, so we knew how to take his derivative? So guess what's going to get easier as we go to section 2.2 and learn rules?
How to find
This one, yeah. But you have to be able to look at the original function and kind of get an idea of what the equation is, and then pretend to take a derivative and see what it would be like. Which means these problems were just an intro to a much bigger issue. Does that make sense? Just an intro. So as we learn more rules, this will get easier. And we have like activities to go through that will help us with, well, visualizing or playing with derivative graphs given original functions. So real quick, guys, can you check your homework? Did you label all of these other dudes F primes?
No.
If you didn't, please label them because they're not F. F is the guy who was given to you originally. F was the original function. We were trying to graph the derivative. All right, we need a quick break. Everybody go back or some person, one representative from every group, going back and get correction papers. And as you do that, I'm going to write down any other homework questions that we have. What else do we have that we got stuck on in homework? 63? Anything else besides 63?
I'll go use a 9 here.
9? Heard of 40 something. You can grab a donut hole, grab a cup of coffee, grab correction papers. We're looking for homework questions if we have any more. It's a big old stack of white papers in the back. Oh, come on, computer.
Oh.
Don't die. Why are we dying?
Actually, yeah, do that. So, John, it's nice to meet you. Are you going to
Okay, we didn't find anything else besides 9 and 63?
Perfect spot, man. Perfect spot.
I know, you weren't expecting.
I thought I gave you harder ones. I didn't.
That's the best. You least expected.
63! Did you watch the video, Kyle?
There's a long story to that.
No.
So I was doing math homework after 11, and my app shut off at 11, so I couldn't watch the video.
Wow.
Oh.
Go watch that video, Kyle.
Hey, I respect that, though.
Yeah,
You can
so-
watch it this morning, but I still respect it.
Oh. Then she's up.
There's a little haunt in
I just turned on. It's fine. So, here we go. Ready?
My app is foggy.
I think we're finding. It's only the minute out and take it. And he dishes it out. He's like, have you done eating my breath yet?
That's mine.
Kyle.
No, but it's true. It's true. I'm like, okay, yeah, you're right. You're right. That was roasting against me, guys. It wasn't against me. Anyway, here we go. Kyle, which way did you go? Did you do h approaching 0 or x approaching 0?
H approaching 0.
Okay. And you guys know why I'm asking that, right? Because the alternate forms aren't there two? F prime of a equals F prime of a equals either F of a plus h minus F of a all over h, or F of x minus F of a all over x minus a. Now, why am I able to spout those off? Because I have them memorized. Now, it's okay. I've been doing this for 12 years. I shouldn't have them memorized. But coming back, what do you need to do? Makes homework easier if you know the formulas. Or at least have your forever cards close to be like, I'm pretty sure they're important. So, F prime of 0 is going to equal, Kyle said the h approaching 0 part, which means you're doing that a plus h, which would be 0 plus h minus 0 plus h squared minus, what's f of 0? Isn't that just 0? Oh, that's easy. Minus 0. All over h. Now, we would normally have to like FOIL stuff if we were doing like the f of x plus h minus f of x, but the nice thing is we can do 0 plus h. What is 0 plus h? Yeah, so that's just 3h minus, and 0 plus h is h squared. This was actually kind of a nice one just because it was so different. But because it was different, it might have thrown you off. I would have reduced h's from everybody or pulled out an h and then reduced, getting 3 minus h. But did you rewrite your limit? If not, you might have forgotten you were supposed to plug in h is 0 to get your 3. Good?
Yep.
Okay. This next one, I'm not going to do the entire thing just because there is a video, but can I set it up? Did you do x approaching -2 or h approaching 0? What were the directions? Just the direction?
Alternate form.
Or was it the same one? Alternate form of the derivative? Did they tell us which one or just go for it? So then you did Abby x approaches a? Like that one? Okay, let's do that one. So the limit as x approaches -2 of f of x, which is nice. I get to just rewrite it. I kind of like this one because of that. Minus f of -2. That'd be -8. 4 and 2 is 8. And then 1. Oh, that's just 1 because those cancel. Now guys, I know I do mental math fast, but sometimes it's my downfall that you guys are like, oh, did you know you're supposed to write an h and you did? That was sick. So be careful going fast, but it will be beneficial if you can. But slow down if you're getting things wrong. 1 minus 1 cancels out, yeah? Factor out that x squared. So you factor out that x squared, what can you now do? What I was always meant to do since the beginning, which is keep going. Okay?
She did. Not for this.
No. That's kind of a common phrase, but it's not.
It sounds too British.
That's always what it was meant to do. It's a little off, but it's not.
Yeah.
You can watch the video. Alright, so whew, there we go. It's the coffee. It's making it fog up a little bit. That's what's going up. Alright. Alright, homework questions. Here we go. Section 2.2a. Basic differential. Ooh, if there's an A, what does that mean? There also is other. Which means it was a hard section that I determined was better to split up.
Which means they're having 2 homework assignments.
Which means there are 2 homework assignments, and probably this is the
First one.
easy one.
Wow.
Yes.
Wow.
And also the easier one.
You're not wrong.
Abby, look, you're still blessing me. Don't judge. I'm a judge. Thanks, Pat.
I know.
Just wish my.
Oh.
So how important is the derivative?
Very.
Why?
Because it's a third of calculus.
It is a third of calculus. What's Kyle referring to? What are the 3 main topics in calculus? The
Derivative.
first thing we learned,
Limit.
limits. Second thing we're learning,
Derivative.
what's that weird SE thing?
There we go.
Integral. Yeah. Integrals. That's that whole area thing that's coming next semester.
Good.
Until she gets to the basics.
No, but then she goes, oh, Yummy.
But out of those 3, the primary mathematical tool is the derivative. Because guess what? Integrals, because of this really cool theorem called the fundamental, just because it's fun, fundamental theorem of calculus, tells me that to find an integral, all I need is to antiderive.
Oh, okay.
So there's deriving, and there's anti-deriving. But what's in both of those? Deriving. Oh. So maybe integrals are really just derivatives backwards. So really just everything does boil down to derivatives. Well, and all derivatives are limits, so really everything boils down to limits. But anyway.
No limits is different.
She seems offended by the compliment.
No, I'm
Right.
really focused.
Derivative is used to calculate and study rates at which one quantity changes with respect to or relative to another. And isn't all of calculus about the math of change?
Yeah.
Change. Things are changing and how they're changing and how fast they're changing and all sorts of change. Now at the bottom of the page is this little thing about Newton and Leibniz. Who the heck are they? Not today, because we've been having a little too much fun, but maybe another day we will talk a little bit more about Newton and Leibniz and talk about the great calculus controversy. Yeah. The great calculus controversy. It was the talk of the town back in the day. It was quite the issue. Before social media. So, Newton versus Leibniz. There were two different guys involved in the foundation, stating the field of calculus, but that is not an issue for today. For today! Oh, you were still writing. I want to get to the fun stuff, so here we go. Basic derivative rules. Hey, I think this was a forever card in your summer packet.
You had a forever card in the summer pack?
Yeah, there were two.
Well, I stopped back then.
There were forever cards. You could have, except you didn't know all the ones before.
She snuck them in.
But, constant rule. Yesterday, did we talk about, Adam, I'm coming to you, what ddx meant? Yeah, derivative, right? So the constant rule, ddx, taking the derivative of a constant. Why? But yes. Why is the derivative of any constant
There's
zero?
no x.
Because what?
There's no x.
There's no x. So you can think of it as x to the 0 power, and power rule says come down. So technically you're kind of cheating and using this rule.
No.
User rule, rule. Uh-oh. So I'm going to actually come back and say why it's always true. But there is this thing called a power rule where the power comes down and then you have x to a reduced power. One lower than what was there before. Which is really, really, really easy to do. Subtract 1 unless the power is a fraction. Well, I would say just do it, except some of you won't even realize the power is a fraction because a fractional power comes from what?
That's right, bro.
Maybe square roots, maybe cube roots, maybe fourth roots. Yeah, I got that. There's a little shout out. But coming back. -1, so easy unless you have a fraction. But even then, it can still be easy if you know it's a fraction. So we have to remember our exponent rules just a little bit. But first, why is the derivative of any constant 0? Because what does the constant function look like as a basic graph? Flat.
And flat.
And what kind of slope is a flat line always going to have? Yeah?
Yeah.
Cool.
Cool.
So if you're going a constant in your car, 40 miles per hour. This isn't at 0, this is up at 40. How fast are you accelerating?
Wait.
You're on cruise control, you're going a constant, 40 miles per hour. How fast are you accelerating?
Not
You're not. Why? Because it's constant. It's not changing. Now, is your position changing?
Yes.
Yeah, you're zoom, 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 right? Well, it's 40. But either way, you can still do some damage. But you're not accelerating. Constant multiple. What do we do? Not you. What if I have a constant times a function? Hey, with limit properties, if we had a constant times a function and a limit, couldn't we pull the constant out and then think of it later?
Yes.
And if all derivatives are limits, then couldn't we do the same thing with derivatives? So maybe we can say this is the same thing as c times f prime of x. Basically, we're taking the derivative of whoever that dude is and just tagging the c along. He gets to stay along for the ride. So constant multiple rule says if we have a function times a constant just gets to chill, and I'll take the derivative of the function. Sum and difference rule. Hey, since the derivative is a limit, if I want to take a derivative of like some sort of f plus some sort of g plus or minus sum or difference, guess what I can do? Take the derivative piece by piece. Step by step. And all of these rules are coming back to those limit rules because derivatives are limits. I know it got squishy, but think about it. The derivative of a sum or difference of functions, I just need to take the derivative piece by piece. Derivative of f plus or minus derivative of g.
School. Wait, is this plus d over d of x?
Of?
On the
Not him,
What's
but
the last thing?
Yeah.
D of x.
That's
See?
d of x.
I'm not sure
because
he
it's
worked
of him
on
plus
flex,
or minus of
so
him.
don't be freaked.
I like all the letters.
Derivative of sine and cosine. Okay, this is interesting.
Oh yeah.
If I was to, you don't necessarily need to write it down. If I was to write the sine curve as my function, my f of x. Okay? And we were trying to find his f prime. Now I know you guys are like, pause. Pause. Do you guys see all these little flat peaks and valleys?
These amplitudes?
You see all these peaks and valleys, all these minimums and maximums?
Yeah.
These maximum displacements which do happen at the amplitudes. What are the slopes to all of those? 0, because they're flat, right? They're flattening points. So my derivative is going to be at the axis. There are going to be zeros there, right? Okay, so sine has zeros at 0 and pi and 2 pi. These are at pi over 2 and 3 pi over 2. Oh, interesting. If you were to zoom in, guess what the slope is right here? 1. Guess what the slope is right here? -1. So that slope is going to be a positive 1. These are not like vertical lines, right? There's slope to it. And if you were to zoom in, the slope would be 1. So guess what? Or who is sine's derivative? Yeah. Cosine is sine's derivative. What? And cosine might be just a little bit harder. Now let's have the graph of cosine. But he has zeros too, right? See the 0 there. Here's a 0 there. Here's a 0 there. Here's a 0 there. Here's a 0 there. What's his slope here? Careful. Downhill slope. And then positive 1. Let's see his derivative is. Sine, almost. Why negative sine? I don't know, you know this? Sine starts by going up. This guy's going down. The derivative of cosine is negative sine. There's a graphical, well, my cosine got a little messy over there, sorry. It was going really well. That's why when we did sinusoidal curves, we had representative points, because otherwise your sines would have looked like some of these things. So we could have had a positive 1, bottom, and then a negative 1, bottom. Anyway, exponential function. Now technically, I shouldn't be showing you this. Because the book isn't going to show you for a couple more sections, then it's going to actually discover it for you, and it's really exciting, and it's nice and it's neat. But it is a basic rule in the sense of it's just one of those foundational things we're going to use again and again and again and again and again. So I'm giving it to you. I'm a little sad because I am, but that's all right. It's a really cool quote that when we discover why he's true, because I can't really show you the whole graph thing quite as nicely. I can, but not really. When I show you why he's true and where he comes from, then I'll use my really cool quote from Francois. Oh, what's his last name? Francois Bibonnet, something like that. Anyway, he has a really cool quote about this derivative rule. The same thing. How do you do that?
That was on the
The derivative of e to the x is e to the x.
That was one of the extra credit questions on the summer package quiz.
What? There's extra credit. On the quiz. Quandary. I was like,
Yeah, there was another.
So I want you guys to go ahead and, well, this is going to be a forever card. Sorry, I didn't actually put a yellow box around it. Forever card number, where are we at now? Because I keep on losing track because it's the
I
different.
lose track.
6, 7, 8, 9, 10. I think it's 10. No, it's not 12. Not yet. That's coming. Oh, man. Guys, we're learning a lot of forever cards, right? Whew, I think we better start studying them.
Study? What is that? Never heard of her.
That's a thing, huh? Okay. What did you guys? 9 was the continuous differentiability connection. 8 was the alternate forms.
I know what I'm doing this
No, the
weekend.
problem solving.
This is number 10.
Yeah, we all-
Yeah, this is 10.
This is 12. This is.
Oh,
Yeah.
I
9 was problem solving clues. 8 was definition of.
You're against me. That's a joke. I really don't like you.
Yeah. Anyways.
No, hands are terrible.
Ready, set. Find me the derivative. And how do we find the derivative? We say the derivative is equal to. Well, you gotta derive, don't you? If there are y's, yes. If there are f of x's, use the alternate. Except, how do you go? Wait a minute. Isn't there a constant multiple rule that says I can bring that -3 out,
Yes.
technically?
Well, why would you do that?
And then, can't I say that I know how to do that because it's a power rule?
Yeah.
So I bring down the 12, and it's x to the 11. So what's my derivative actually going to be?
-3, 6, x to the 11.
Dun, 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 dun. Now, did I take quite a bit of time to do that?
Yes.
Yes. Could some of you possibly get to the place where you just bring down the 12 and say, oh, hey, there's a guy waiting for him, so -3 times 12 is -36.
You still want to put that?
X to the 11. Just don't make mistakes. I don't mind you going fast if you're doing it perfectly. If you guys are ready, go derive number 2.
Don't drink and derive.
Oh, shoot.
Thanks, Adam.
Does every year student come up with what goes on the pancake?
Yeah.
Last year was quite the debate. The two classes had very differing opinions, and then finally Hina Tangaya and who else was in here?
Concert.
Nicholas Hartman.
There were like 3 people that were in here, and they finally were just like, we're making our own design, they better agree on it. So they just like scrapped everything that everyone had said, and then they made a design, and they were like, okay.
What was last year's one?
It was the Pokemon one.
Oh, if you don't talk to my
What?
son,
I don't
my
remember.
son's son, or my son's son.
I didn't
You guys could
understand
actually understand that one, the sun, and the sun, and then you could understand last year's too.
I like how crazy deriver is.
I have 2 years ago ADP. Wait.
Yeah.
It was in the past 2019 was an
Wait, what are you guys doing to this guy?
Oh.
Do I do it there?
Oh, that's funny.
Where did it come from?
That's intensity.
Wait, what?
So here.
Wait, so then it would just be 2x cubed.
Is this legal according to my properties above?
Is it even legal, my lord? Oh, man.
Just
Sorry.
Anyway, can't I bring a constant out from constant multiple rule? Can't I take the derivative of whatever is remaining, the sum or difference, separately? So can't I use the power rule for this guy, bringing down the 4 and making the x to a decreased power of 3, and then the derivative of any constant is 0. So my final answer would be 2x cubed. What's another? Yeah, it is. What's another way of writing this though that you've also thought about first?
You distribute.
You can go for it the way it's given to you, or you're gonna start learning. You can
all over 2.
1/2 x to the 4 plus 7. And then we could have just done the sum and difference rule and said, oh, hey, bring down the 4. 4 over 2 is 2. 2x cubed plus 0.
What would actually be like more sense?
We're going to be rewriting it. Sometimes we're going to have to rewrite it, like it's a necessity. And this one you didn't have to rewrite it. You could have gone for it the way it was and just thought constant multiple rule and sum and difference rule all at the same time. But distributing could have been nice. Distributing could have been helpful. Well,
Hey, this is where I'm the section of the chapter.
here's the dealio.
Guys, I'm in the section. Relax.
Here's the dealio. Let's see what other pages we have. Oh, 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 oh. Hey, what's the majority of the section? Can't show you that yet. Oh, do you guys see how many examples we have? So why do we have so many examples?
There's a lot of basic rules.
Because it can get hard. Guess what? Basic rule, basic rule, basic rule, basic rule. That doesn't look like a basic rule. We did not do division. We did not do multiplication. We did not do... Oh, wait. What did I tell you about this guy a second ago? He's a fraction. He's not a fraction. Oh, his exponent's a fraction? So we could rewrite this as negative. Now, I'm not deriving it, so I'm not pulling up the red. I'm just rewriting it. I could make this x to the what power? 2. It's a power rule? The constant could stay. The 2/3 would have to come down. I wonder if you guys can actually do that. And then I need to subtract 3/3. No, that's not what the power rule says. The power rule says -1. Yeah, I know. On your brains, what's going to be easier to subtract from 2/3? 1 or 3/3? So you're going to need to train your brain not to always just think 1. I mean, always think 1, but in different forms, right? Yes, that is. We covered most of the notes for homework, but we haven't gone over everything. Guys, I have your test. Real quick note. This is with me getting quite a bit of partial credit. Some of you skipping either entire problems or just getting like big problems wrong. I'm going to say your name as you can walk out the door. But this does not include the bonus practice test. It's put in a separate category, but if you did that well, you can think of add 3 points to the score. That's what's going into your test quiz category. And we only did 1/3 back on your summer review quiz, so you could get half points back on this one. Because for some of you, this might be the lowest one of the year, because you're like, oh, calculus is different. Yeah? So, if you have a bad score, just take a deep breath. Come talk to me if it's going to help you calm your nerves. And I've talked too long. Abby, come on up. Vicente, come on up. This is in no particular order. Kathleen, come on up. You can grab it on your way out the door. Nehemiah, come on up. Austin, come on up. Kyle, come on up. You can come on up and go straight out the door, guys. Bring your stuff up. I don't mind.
Sorry.
Kyle, Alfredo, John, Adam, Madison.
Kyle.
Austin, Alfredo, Nehemiah. Oh, Nehemiah's gone. John, Adam, Madison. I just told everyone to safer that way. Andrea, Mariah. Remember, you can add 3 if you get that bonus test. Wyatt, Rico. Oh, and James Page. Bye, kids.
What?
I haven't scored them yet, Gavin, so I'm going to pop by after school just to check and see if I got it down. Class notes?
Just be honestly, the number